What is solar energy? Solar energy is simply energy provided by the sun in the form of solar radiation, which makes the production of solar electricity possible. Electricity can be produced directly from photovoltaic or PV cells. Photovoltaic literally means light and electric. These cells are made from materials which exhibit the photovoltaic effect. This means that when sunshine hits the PV cell, the photons of light excite the electrons in the cell and cause them to flow, generating electricity. Solar energy provides electricity when it is in demand during the day, particularly hot days when air conditioners drive up electricity demand. In use, solar energy produces no emissions. 1 megawatt hour of solar electricity offsets between anywhere from 3/4 to 1 full ton of CO2. The basic science behind solar energy collection dates back to the 1930s. However, the first commercially viable silicon solar cell didn't become available until the 1950s. Many scientific innovations have led to the modern PV systems and made them much more economical. PV panels are being used increasingly both in the city and in remote locations to produce electricity for households, schools, and communities, and to supply power for equipment such as telecommunication and water pumps. Solar panel systems can be small or spread over acres for mass collection. Generally, the principles are the same regardless of the dimensions. As an example, silicon-based solar panels are installed on house rooftops. They capture the sunlight and convert it to direct current or DC electricity. Most appliances are designed to run on alternating current or AC, so the DC power must be run through an inverter before most homes can use it. If a home is equipped with a bidirectional utility meter, when more electricity is produced than may be needed, the meter literally runs backwards as the excess electricity may be sold back to the utility company. At night or on very rainy days, the utility meter of course allows the transmission of electricity from the utility grid back to the home or business requiring power. All renewable energy except tidal and geothermal power ultimately originates from the sun. The Earth receives 1.74 times 1017 watts of power per hour from the sun. Up to 2% of this energy is converted to wind energy, which is about 50 to 100 times more than the energy converted to biomass by all plants on Earth. Geothermal energy is the heat contained in the Earth. It's clean and sustainable. Resources of geothermal energy range from the shallow ground to hot water and hot rock found a few miles beneath the Earth's surface and down even deeper to molten rock known as magma. Another renewable resource is hydroelectricity. Hydroelectric and coal-fired power plants produce electricity in the same way. In both cases, a power source is used to turn a turbine, which then turns a metal shaft in an electric generator. It is this generator that produces electricity. A coal-fired power plant uses steam to turn the turbine blades, whereas a hydroelectric plant uses falling water for the same purpose.
Our renewable energy portfolio and its recommendations will be concentrated on solar energy. Solar energy is the cleanest, most abundant renewable energy source available. The U.S. has some of the world's richest solar resources. Today's technology allows us to harness this resource in several ways, giving the public and commercial entities flexible ways to employ both the light and heat of the sun. In order for us to smoothly transition over to using renewable energy such as solar energy, we must make it affordable not just for big corporations, but also individuals who wish to install solar technology in their homes. Currently, the cost to install solar technology in a home is prohibitive for most. Commitment to sustainable energy policies will require incentives and tax breaks in the hope of motivating individuals and businesses to move towards this direction. These are our recommendations. Set incentives for payback targets. The incentive levels should be set so that solar system owners recoup their system costs over 5 years for commercial customers and 10 years for residential customers. Encourage efficient system designs. Where possible, incentives should reward high-performing systems. Direct incentives can be adjusted to encourage systems that maximize peak energy production. A performance-based incentive is based on the actual energy production of a system. This will encourage active and ongoing maintenance on these systems that are installed in businesses and homes. Phase out incentives over time. One of the main reasons for enacting solar programs is to jumpstart a local solar industry. As the market grows, costs will decline through increased sales volumes and competition. Developing local markets is critical to building a large-scale national solar industry in the U.S. As the installed cost of solar declines, incentives can decline as well. New solar customers will still maintain the payback target described above, and eventually the industry can thrive on its own and incentives are no longer necessary. Offer solar investment tax credits. The ITC reduces tax liability for individuals or businesses that purchase qualifying solar energy technologies, encouraging investment and spurring growth in solar energy. Offer leasing agreements along with purchase agreements. In the lease model, a customer will sign a contract with an installer or developer and pay for the solar energy system over a period of years or decades rather than paying for the power produced. Solar leases can be structured so customers pay no upfront costs, some of the system cost, or purchase the system before the end of the lease term. Similar leasing structures are commonly used in the many other industries, including automobiles and office equipment. For example, in the city of Hillsborough, over a 20-year solar lease with no upfront cost, an average household is estimated to save about $5,000 on energy use. Here we have a simple solar investment payback formula. This means a 6 kilowatt grid-tied system on average costs about $10,000. And that's obviously a subject to market fluctuations, including fees and incentives, tax breaks, and so on. The average U.S. household uses almost 11,000 kilowatt hours of electricity a year. They pay an average of 12 cents per kilowatt an hour for it. Assuming typical sunshine conditions of 5 peak sun hour a day, this system would pay itself back in roughly 8 years, give or take a few months. Now, this brings me back to the average savings I spoke about in the city of Hillsborough. Knowing now that this formula takes into account a typical day with at least 5 hours of sun, we can easily see that although $5,000 in savings over 20 years may not seem like a lot in the state of Oregon, this could translate into huge savings in states such as Hawaii and California, where the sun is abundant. This chart shows the U.S. energy consumption by energy source in 2014. With the recommendations that I have stated previously, we are hoping that within 20 years, instead of only 4%, we will see an increase of 25% or more in solar energy consumption alone.
Because the source of solar energy is the sun, and current estimates place its life at another 5 billion years, this portion of the solar equation will not be depleted in mankind's foreseeable future. Silicon resources for photovoltaic collection are finite, but technological advances are reducing the quantities needed through thinner application processes while maintaining energy level production. With thinner applications of silicon able to capture the sun's energy, new methods of application such as painting or spraying opens up even more opportunities for use in places originally considered unusable. This also goes hand in hand with increasing the efficiency of both the actual cells and of production methods to reduce the ecological footprint toward full sustainability. Using ever smaller amounts of crystalline silicon to create PV surfaces is one option when faced with a finite quantity of a critical component. Another option, with an ever greater focus on sustainability in all parts of the renewable resource equation, is to develop other composites which can replace silicon. In 2012, Stanford University researchers demonstrated a method of constructing PV cells from carbon nanotubes comprised of graphene. They posited that carbon for this purpose is completely renewable and is even available from incinerated trash. Let's take a look at solar energy's return on investment, or EROI, to compare it to past and current fossil fuel sources and other renewable energy sources. For solar, this means how much more energy does a solar panel generate in its lifetime than is used to create it, install it, and maintain it. When comparing various energies' return on investment, as adapted from 2010 findings by EROI research pioneer Dr. Charles Hall, PV solar has a fairly low return, less than 10 to 1. This may seem to make it less desirable as an alternative energy resource. However, many recent studies have shown an increasing EROI as technologies advance. This encourages more people to install panels, and that reduces ongoing production cost. This then brings solar EROI, especially related to PV solar, back into the running. Based on current technology and ongoing advances, solar energy, especially PV solar, is a viable option in the renewable resources category for power generation. Based on current or near future energy returns on investment, solar cannot unilaterally replace global or even U.S. reliance on fossil fuel or energy derived from coal resources. However, it is an important part of the combination strategy to replace finite energy sources with renewable options, which leads to this recommendation of 25% of the U.S.'s total energy production being met through the use of solar resources by 2035.